Here is a mass spring system. It's oriented vertically, not horizontally, but it still oscillates with simple harmonic motion. So if I pull it back and let go, up and down it goes, oscillating back and forth. Spring 3 has the same mass, 100 grams. It has the same spring constant, the same stiffness. So if I pull it back and I let it go, it will oscillate with the exact same simple harmonic motion. These are the same, right? Well, not exactly. After all, when this one goes up, this one goes down. It's kind of like they're at opposite moments in the cycle. They're not synced up. In IB physics, we would say the two systems are out of phase, or the term we can use is antiphase. What is phase? It refers to where the system is in the cycle. Is it at the beginning of the cycle, or is it halfway through? We can plot the motion of these two springs using displacement time graphs. So here's the first spring. It starts at 0 displacement and then it moves to the right. And then it goes back to 0 and then it moves to the left. But if we look at the second spring, it's not at the same spot. Now this is a different scenario from what we just watched. Here, the phase difference is not exactly halfway through the cycle. How do we find the phase difference from these graphs? You identify a distinct peak. And once I choose, okay, I'm going to look at the very first peak, I find the same first peak on the bottom graph. The phase difference, phi, is how much phase separates those two peaks. They should be at the same spot, but they're not. To answer that question, we're going to need some grid lines. First, let's answer the question, how much time separates these two? Okay, well, the first spring reaches max displacement at 3 seconds, and the second spring doesn't get to that same position until 5 seconds have passed. So, how much time separates them? How much time are they off by? 5 minus 3 is 2 seconds. That's not quite the phase difference, though. Phase difference is asking, how much of a cycle are they off by? So I have to take the whole cycle and consider this tiny sliver in green. What fraction is it of the whole cycle? Okay then, the whole cycle, that's the period. So if I divide by the 12.5 seconds that this whole cycle lasts, I look and see where does the cycle end, 12.5 seconds. Now I know what fraction this 2 seconds represents. It's not a very big part of the whole 12.5. So the springs are pretty close to each other in phase. There's not much difference. Now we could stop there and express phase difference as a percentage or just a fraction. But instead we use radians. How many radians are in one full cycle? The answer is 2 pi. So when we multiply the fraction by one full cycle, we get the phase difference in radians. And in this case, it would be 1 radian. The formula we've just discovered for phase difference is phi equals the amount of time separation between the two displacement graphs divided by 1 period. This tells us what fraction of a cycle off are the two springs. But instead of leaving our answer in a fraction, we multiply by 2 pi radians. This is the formula for phase difference, and it's unfortunately not provided in the IB Physics data booklet. Let's try an example. How much phase difference separates these? Pause the video and take a look. Okay, the first thing I do is I say, here is a peak that I can recognize on both graphs. Right here, the peak occurs at 7 seconds, and here it is occurring at 8 seconds. So the time difference is 1 second. What is 1 second relative to a full cycle? Well, the full cycle starts here and it ends at 8. So I start with a phase difference of 1 over 8. This is the time difference, that's the period. And then I multiply by 2 pi radian to turn this phase difference from just a fraction or percentage into some number of radians. What's my answer? 0.79 radians.